Let's talk about the appeal of autonomous AI agents. The promise is that you can drop an agent into your enterprise and it will seamlessly connect to your previously isolated workflows, moving across barriers to accelerate your operations without human bottlenecks. To make this work, organizations are handing these agents broad, cross-system read access. We're giving them the credentials to look across our repositories, including private ones, so they have the context to actually assist us. But a recent exploit discovered by Noma Security, called Get Lost, shows exactly how fragile this setup is. Their researchers found that an attacker doesn't need stolen credentials or server access to compromise an agent. They just need to open a standard public issue on a repository. Because the agent is designed to read and respond, it processes that public issue. The researchers proved that prefixing a hidden instruction with a single word, additionally, was enough to bypass guardrails, tricking the agent into pulling data from a private repository and pasting it straight into a public comment. This proves why treating AI agents like standard software is dangerous. Traditional code executes strict logic. Large language models process natural language, which means they cannot reliably separate the instructions you give them from the data they happen to read. This exploit relies on an architectural vulnerability known as the lethal trifecta. First, the agent holds credentials to read private data. Second, it is exposed to untrusted public input. Third, the agent has a mechanism to post publicly. Combine these three, and you create a direct path for data exfiltration. The model can't distinguish safe data from malicious prompts. Traditional InfoSec tools and vendor guardrails are built for deterministic threats. They look for known bad code or unauthorized access. They struggle to catch natural language manipulation, where a seemingly routine request forces the agent to misuse its legitimate permissions. Securing enterprise AI requires moving past reactive patching. You have to step back and implement comprehensive structural risk governance before you even deploy the model. If you look at the research, the sheer volume of theoretical AI threats is paralyzing. This diagram represents the MIT AI Risk Repository, which catalogs 1,835 documented entries. It's an overwhelming list for any governance team to tackle. A large portion of those risks involve model alignment and pre-training decisions. If you are deploying a system built by someone else, those foundational issues are entirely outside your control. You have to stop trying to manage them. Instead, the Deployer AI Risk Register narrows this down. The first filter isolates threats from your own configuration and operation. The second keeps only items you can operationally measure, dropping the noise to exactly 82 specific risks you can act on. The trade-off here is straightforward. Executives must accept they cannot fix the underlying flaws in a third-party model and focus their resources on mitigating the operational outputs within their own environment. Once you have that deployer-scoped list, you run into the next hurdle. AI risk is cross-disciplinary. It cannot sit on the desk of a single, siloed AI safety team. The DAR maps those 82 risks into 7 families, aligning with existing enterprise domains. Model behavior issues map to the Chief AI Officer, security threats fall to the CISO, and regulatory compliance belongs to governance, risk, and compliance officers. By dropping AI risk into your existing governance structure, you prevent a bottleneck. It simply requires extensive cross-training for your traditional InfoSec personnel, so they know how to evaluate non-deterministic threats. Let's apply this deployer-scoped governance back to our initial threat, the Get Lost vulnerability. Knowing the risk sits with the CISO, what is the specific technical response? Because the model itself cannot reliably filter out prompt injections, you have to enforce strict architectural boundaries. That starts by severely limiting cross-repository access. This requires a practice called token scoping. Instead of issuing an organization-wide read token for convenience, you restrict the agent's read access exclusively to the single environment or project it is actively triaging. Next, you must break the exfiltration channel. Any public-facing output generated by the AI agent must be gated behind a mandatory human-in-the-loop review process. This is architectural isolation. By controlling access and cutting off the automatic outward flow, you stop unauthorized data movement, trapping the threat before exfiltration occurs. But this introduces a harsh trade-off. Dismantling the lethal trifecta significantly degrades the autonomous speed of the agent. You are deliberately trading away some of that AI magic to reintroduce operational friction and safety. AI risk management has matured out of the experimental research phase. It is now an unavoidable architectural and compliance mandate. This matrix maps out your governance stance based on your specific risk appetite, comparing high autonomy on the y-axis against high security on the x-axis. If your DevOps teams prioritize pure speed and rely solely on the vendor's AI filters to stop prompt injections, you're leaving your private repositories exposed to any attacker who can write a public issue. Conversely, if your organization requires high security, you have to trade away broad agent permissions and commit to enforcing manual review checkpoints at the edge of your network. True enterprise protection requires matching your chosen governance stance precisely to your organization's tolerance for data exposure. The good news is that you don't have to reinvent the wheel. Frameworks like the Deployer AI Risk Register already map these threats to international standards and existing corporate roles. But you have to accept the reality of the supply chain. Running an AI system built by a third-party vendor does not offload the liability to that vendor. When an agent operates within your environment, accessing your data, the deployer ultimately owns the outcome of any action it takes. Assume the AI will eventually be tricked. Structure your operational boundaries and access controls around that certainty, and you protect the data, even when the model fails.